Yeah, so I'm glad to welcome everybody to our industrial seminar, and I'm happy to introduce Philipp Hennig from Tübingen, who will talk about probabilistic numerics today. And now, Philipp, I give the floor to you.
Thank you very much. Well, so thanks for the invitation. Thanks to all of you for coming. I'm just gonna start. You've seen the title. Well, actually, since there's such a manageable crowd, who of you have heard of the term probabilistic numerics before? Just, I don't know, raise your visible hand or something. Okay, so that's almost everyone. Good. Let me see if I can give you my introduction for it, which of course people might have different opinions on. So I'm even though the title contains the word numerics, I'm actually in my group. We are working we're at home in computer science, and we're publishing in the machine learning community, and we feel very much as sort of computer science machine learning researchers. But of course, you could call this field by many other names as well, right? Like data science, computational statistics, whatever. All of these are fields in which that you could think of as building algorithms that refine a model through data. And that's actually a description you hear for machine learning in the popular representations of it often. Now, but both of these things, the model and the data, are things that enter from the outside world. The model is provided by a human user or expert, and the data comes from the physical world. But what actually happens in the computer is, of course, a computation. And in contrast to classic AI, rule-based AI, which typically did tractable, discrete computations, contemporary machine learning is characterized by numerical computations. And by numerical, I mean the computation of quantities that don't have closed form expressions, so that can only be approximated in finite time. There are integration problems for all of probabilistic inference, so to compute marginals, conditionals, posterior distributions. There are optimization problems to fit estimators, to minimize empirical risks. There are the solution of differential equations, so simulation methods, to predict what happens next, what happens in the future. This is important for concretely for fields like reinforcement learning, but also more abstractly for scientific applications of machine learning, for econometric applications, industrial applications, and so on. And of course, linear algebra for all of the above, because linear algebra is the base case for everything, for the solution of Gaussian integrals, quadratic optimization problems, least squares problems, and the solution of linear differential equations. And for all of these problems, of course, there are methods available to address these problems that have been around for much longer than the term machine learning. They were invented 20, 30, 50, maybe 100 years ago, depending on which of these tasks we talk about. And they are widely used in our field as algorithms that arrive in our field as toolboxes, as black boxes. And that's actually going to be a theme I'll return to over the course of this talk, that many people in machine learning, at least at the moment still, think of these numerical algorithms as tools that are part of typically a Python library, and you don't think much about what they do. And what I'd like to convince you of today is that this is maybe not the ideal approach to take, because contemporary machine learning problems have some aspects that distinguish them from the tasks that these algorithms were originally invented for. And I'd like to highlight a few of these aspects. A first one is that maybe you can think of the generic machine learning problem as empirical risk minimization, so the training of a deep neural network, if you like. That's like the poster child of machine learning at the moment. So you can think of a loss function that's an objective that happens to be a sum over a large number of terms, where each term depends on a single datum in the data set and all the parameters of the model. So the parameters of the model could, for example, be the weights of a deep neural network. You can also think of this loss as the logarithm of a likelihood function that doesn't really matter for what's to follow. And so one first aspect that is sort of maybe characteristic of contemporary machine learning problems is that theta is extremely high dimensional. So the number of parameters is often chosen such that it just about fits into the memory of whatever the machinery is, the GPU cache, for example. And so that's not really much of a problem, but it causes a few problems, like, for example, that it's difficult to keep track of a tail of several observations. For example, that means that it's hard to build low rank approximations, like, for example, in quasi-Newton methods. But overall, that's actually maybe not the biggest challenge. The much bigger challenge is that the data set is also large, that the number n is a large number. That's the technical, for me, that's actually what the word big data really means. So whenever your numerical algorithm, let's say an optimizer, for example, wants to compute a gradient of this loss function, no one actually goes through the whole data set to compute this sort of, let's call it like a full batch risk. But instead, people subsample the data to get a mini batch evaluation of this loss function. And what that means is that what you actually get, so this batch is drawn IID typically from the whole data set, right? So what you actually get is a random variable that is only equal to the thing you're trying to compute in expectation. So it's typically an unbiased estimator, but it's really a random variable. And because m, the batch size, is typically very small, so in typical applications, m is like 1 or 64 maybe, because these numbers are so small compared to the overall size of the data set, this random variable tends to have a very large variance. So this is a severely stochastic kind of problem. Severe in the sense that typically actually the standard deviation of this random variable is larger than the mean. So if you think of so classic stability analysis for numerical algorithms basically assumes that whatever the algorithm is trying to compute, it computes that number and then it gets perturbed by a small amount. There's a small mistake being made in the computation, and then the analysis is about how does this small mistake sort of propagate through the computation. But when you are in a setting where the error is larger than the value you're computing, then this is really not a meaningful approach anymore. So you can't really think of like a local Taylor expansion to analyze what's going on. It's also because another way of thinking about this is that because if you actually manage to draw IID numbers here, and if m is sort of reasonably large, then this is a sum of IID random variables. So what we're basically computing here is a likelihood for the unknown quantity that is roughly Gaussian distributed. So it's a probability measure. It's not a point mass. That to me is actually the main challenge in to the computational use of numerical algorithms in machine learning. And there's a third challenge, which I'd like to teaser now already and then return to later, which is that quite often now increasingly the kind of information that you would like to use in a machine learning task comes from multiple different sources of information that I might want to describe as mechanistic and empirical in nature, where the two different kinds of information are linked together by a computation that is of numerical nature. So, that sounds a bit abstract maybe. Let me give you a concrete example. So here is a very 2021 data set that all of you have seen a variant of. So what you see here at the top are COVID case counts in Germany over starting from the beginning of the pandemic to early 2021. I've deliberately, for this paper, we deliberately this is going to be it's actually a NeurIPS paper this year, and we deliberately take the data only up till May this year, that to avoid people trying to turn this into some kind of political advice about how to work with the pandemic, right? So it's really just a use of this data set to explain what's going on. So if you just have this data, so if someone just gave you this time series, and then you apply your standard toolbox, graduate level toolbox of machine learning to it, for example, Gaussian process regression with a standard kernel, I guess we all agree it's not going to work, right? You're going to get an extrapolation here, because the question, of course, is about extrapolation typically, right? So what you'll get is just a straight line maybe, or if you use a stationary kernel, something returning to a mean or to 0 maybe, or just linearly extrapolating. None of those are interesting for the kind of questions people actually want to ask about this data set.
Why is it oscillating in the first place?
So this is a feature of this data set, and these are the weekends. So all of the vertical bars are Sundays, and in Germany everything shuts down on Sunday, so no one reports anything. So of course you can fix that, right? That's not really a challenge, right? I think all of us can think about how you would deal with that. It's more that this overall shape is the real challenge. So we have another form of knowledge about this problem, and that's a mechanistic one, a scientific one. We have a model for what's actually happening there, and that's described by an ordinary differential equation, this famous SIR model or a variant of it, which is a differential equation that says that you can separate a population into, let's say, 5 groups: the susceptible, the infected, the recovered, the vaccinated, and the dead. And so what happens is that people move from one group to the other. So you start out susceptible, and then if you have a contact with someone who is infectious, then you move with a certain probability that depends on a contact rate beta, so it's like how often people actually meet, then you move into the infected group, and then out of that you move into either the diseased or the recovered group, and maybe you get vaccinated, and you can also move, like jump directly without getting the disease. Nice. So the problem with this approach is that we don't know beta. If we set beta to 1, we get this famous curve that everyone was looking at in like early 2020, where you just get an exponential growth until everyone's infected and then it dies back down again. We all know that that's not what actually happened because of lockdown measures, because people reacted in a personal level, and that changed beta. So beta is really a function that changes over time. It's not just a constant. Clearly, right? We can see from the shape of this curve. So here we have two different sources of information we'd like to combine. We'd like to both use the fact that we have this data to learn about what beta is and use our knowledge about the ODE to predict better what's actually going to happen. Now, of course, there are approaches to do this that are not of probabilistic numerical nature, and I'll get to those in a moment. But I just want to highlight that those are challenges to the numerical algorithm, or the numerical domain, that the kind of computations we'd like to do, they don't necessarily fit into these traditional frameworks of forward and inverse style inference. So we have new computational needs in machine learning, and we need to address those. Now, you could, of course, say that, okay, that's a task for the applied mathematicians. We'll stay away and wait for them to find out what needs to be done. But I think there's a good reason for the two communities of applied mathematics and, well, let's call it computer science, machine learning, to interact and share information, because not only does machine learning need new numerical algorithms, it also turns out that you can think of numerical algorithms as learning machines. Because a numerical algorithm estimates an unknown quantity, like, for example, the value of an integral, given evaluations of tractable quantities, like, for example, values of the integrand, even if they are corrupted by noise, like I just described before. So they're estimating latent quantities from observable quantities, estimating unknown quantities from data. It's just that we are used to data coming from the hard drive or from a sensor, and here in computation, data actually comes from the CPU or from the GPU. But that doesn't really matter, right? It's just a number. Where that number comes from is not philosophically relevant, maybe. And that means we can think about numerical algorithms in the language of machine learning, and we can phrase them in particular in the mathematical language of probabilistic inference, as algorithms that take a probability measure as their input rather than a point mass description, then use Bayes' theorem, probability theory, to refine that probability measure in the light of computations that they perform themselves, and then return an output as an output, again, a probability measure rather than a point estimate. And these algorithms we like to call probabilistic numerical algorithms. This insight that computation can be thought of as inference is anything but new. It was already used by Henri Poincaré in his analytic theory of probability, which is arguably the invention of probability theory, or at least a very early version of it. I don't want to take away anything from Kolmogorov, right? But and it was repeated over and over again by various statisticians over the years. But I think in the last decade or so, this idea has taken on a lot more steam, driven, actually, in my opinion, largely by this challenge that computer science has entered a phase where the problems are harder, they're different, they are typically of a probabilistic nature, and the people doing those computations also tend to think in probabilities. So there's a more useful connection. So I also wrote that in the abstract for this talk. What I'd like to focus on for the rest of this talk is specifically simulation methods, so solutions for differential equations, because that's just one area where there's some interesting developments that I can focus on. But of course, this research has been done in all of these 4 areas, at least, that I've mentioned above. So let me now focus on differential equations. Actually, particularly ordinary differential equations. I can say something at the end, if you like, about PDEs as well. So to get everyone on the same page, what I'll be talking about is the solution of ordinary differential equations. So that means we're looking for a curve, x, that is has a scalar input and a multivariate output. There's an unknown kind of this black thing here in this plot, right? And the only thing we know is A, that the time derivative of this curve is implicitly defined through this vector field f, which you can see as this kind of quiver plot, these arrows here in the background. It's implicit because x shows up in f. That's what the entire point is of this problem, right? And the other thing is that we happen to know that this curve starts at some point. So it's an initial value problem. So, of course, there are classic algorithms to solve these kind of problems. There are many of them, and you can find them in standard toolboxes. But imagine you had forgotten about these methods for a moment. Then you could think of those as a machine learning problem. And it's actually a recursive kind of problem. So we know that this curve has to go through this x0. So we know that it goes to this little black dot here at the end. And that means we can evaluate f at that point. And what we effectively get is an observation, a datum, a data point, that tells us something about the gradient of this curve at that point. So we could use that to condition a prior measure on this first observation, and that might give us a posterior distribution over the solution of the ODE that we can use, for example, to predict into the future what the solution of the ODE might be at some, or this initial value problem might be at some future point. And then evaluate again at that point to get a noisy observation of the derivative of this ODE at that point. And we can then continue iteratively forward in time so that once we reach the endpoint, we have an estimate of the solution. So that's this red curve and a posterior probability measure surrounding it. And so if you think of a classic ODE solver, then of course these methods don't work exactly in this framework, but their nature is very similar. They have this recursive nature that they iterate between extrapolating and observing. And the stuff you hand to them, so here is like a typical ODE solver, the inputs you give to them is a handle to the vector field, the span of time points, so basically the beginning and the end of the region you want to integrate over, and the initial value. And what you get as an output is this red curve in the middle, this estimate for the solution. So what I can tell you is that there is a replacement for this method, a probabilistic set of ODE solvers that also return this red line, or actually something very similar to it, very similar in the sense of both computational complexity and convergence rate. So computing this red line is as expensive, linearly expensive in the number of steps as the classic methods. And if you increase the computational resources afforded to this algorithm, then it contracts towards the black line at a high polynomial rate. So for classic ODE solvers, high means, well, okay, for the ones that most people use, means 5. But there are, of course, higher order solvers of order like 8, 9, 10, maybe even 11, right? So the red line contracts to the black line at a high rate. But there's this new thing around it, this probability measure surrounding this estimate. And it turns out that we can also show that the contraction rate of that measure around the estimate is a worst case bound under suitable assumptions for the distance between the black and the red line, basically, right? So for the actual estimation error. So that's the sort of the high level pictorial view. Now the question, of course, is what are these algorithms? What do they actually look like in practice? Well, they are filters, Bayesian filters and smoothers, or Kalman filters.
Excuse me, can you go back to the previous slide? I have a brief question, if you don't mind. So here, the samples which you show here, the trajectory, yes, these are non-Gaussian. So you probably model something as a Gaussian process inside, but these actual samples, it's just that they don't look Gaussian.
They actually are Gaussian. Okay, so I should say a few words about them. So if you freeze the video at any point, then they are draws from a Gaussian process. And the way that I do this animation is that I draw from a standard Gaussian, draw a great circle in this standard Gaussian on the plotting grid, and then map through the covariance and add the mean. So that means every frame of this video is equally likely. And if you stop the video at any point in time, you get a valid sample from the GP. But the dynamics, right, of this through time, they are like they reflect the shape of the posterior, but they are not along the time axis. They're also Gaussian samples along the time axis, but they are not related to the I don't know what they are not related to, but they are, like this animation kind of gives a feeling for what kind of solutions are like equally likely, basically. Mm-hmm. But it's a Gaussian process, and actually, it's a very good question. I'll tell you why it's a Gaussian process. if you want, right? Or
the equation is probably linear, and this is why it's Gaussian.
yes.
Yeah.
So this is exactly. So this is no. Actually, this. You're very good question. Let me get to that. So here I'll tell you how these algorithms work, and then maybe it'll be easier to explain in which sense this is a Gaussian process. So if you are like if you forget for about the ODE setting for a moment, if you do Gaussian process regression, then what you're doing is you're assigning a stochastic process, so a probability measure over a space of functions, and then assuming you're evaluating a deterministic function, you are refining that probability measure, right, to contract around the deterministic function. It's just that what we now do is we replace function with differential equation. So we're going to model a intractable, nonlinear, ordinary differential equation. So intractable means there's no closed form solution. Nonlinear means there's no analytic solution, right? But it's an ordinary differential equation, so it's not stochastic. It's a deterministic thing. And we're going to model it by putting a prior over it that is a stochastic object, just like you put a GP prior over an unknown function. But it's a tractable model, a linear Gaussian stochastic differential equation. So that means the solutions of that differential equation form actually sample paths of a Gaussian process. And so more specifically, we're not going to use any Gaussian process, but we're going to use a Gauss-Markov process. So a Gaussian process that can be described through a stochastic linear differential equation, or it can also be described as a Markov chain of a set of states that like change through time. And we'll call those capital X, where you can think of capital X indexed by something as a vector of states. It's also called a state space model sometimes, such that the zeroth state of the zeroth entry of this vector corresponds to the actual solution of the ODE, and the higher order states correspond to higher order derivatives of the ODE. So the first entry in the vector, the zeroth entry is the solution, the first entry is the derivative, the second entry, and so on. And then we describe our prior. So usually, I mean, in regression here, you would write P of X is Gaussian process with mean and covariance. For stochastic differential equations, we write like something like this, right? A linear, actually it may be a time varying, but a linear stochastic differential equation where dw is the Wiener increment. And now, so inference in such models can be done using Bayesian filters and smoothers. So that's a forward-backward pass on this graphical model, essentially. And of course, so far I haven't told you yet what the data is. The data is going to be this numerical piece of information that the derivative of this curve x, so the first entry in this vector, is equal to an evaluation of this nonlinear function at the true solution x, so the zeroth entry of the vector. And we know that that's the case, actually. We assume that we really know that that ODE is correct, so that means there's a Dirac measure here. It's like this connection is tight. We call this the information operator, thanks to a paper by Philipp and others. Great. So okay. I just see your question. I'm going to get to this Markov property. Okay. So now the only challenge now is that we don't know what x is, right? X is actually a random variable, so there's a probability measure over x. So this likelihood is again implicit. So what we do is we marginalize over the unknown x, or at least you would like to do that. So there's an integral going to be over p, right? Integral over this, px dx, basically. But because, so that's nice with a Dirac measure, right? You can imagine that that's going to work. But the challenge is that f is a nonlinear function. So what we do is we approximate f with a linear function, for example, using automatic differentiation, or a quadratic function, or any higher order polynomial, if you like, right? Using automatic differentiation. Typically, we do it up to a linear sense, and that then gives rise to the so-called EKF1 algorithm, so the extended Kalman filter of first order. For those of you who have worked with Kalman filters before, you know that they look like this. If you haven't, then it's going to be hard to parse this. But basically, in the signal processing community, these algorithms are always written in this form. They always use exactly this notation. So the fact that there are A's and M's and P's and Q's in here has like significance because these words are widely used, or these symbols. And really, the main thing I want to get across here is that this is a for loop. There is a for loop around this whole thing that always steps one step forward to make a prediction, then you can make an observation of this information operator that happens in here. So this first two lines is the prediction. Then you make an observation that gives an updated estimate here of the state. And then you can step forward again and predict. And once you're at the end of the chain, that's like the first part of the sum product algorithm forward. Now you can go backward again. So there's a step that's called the smoother that I'm not plotting here, which does not have to touch the data again. It just is a quick like bookkeeping step that goes back. So this entire algorithm is O of n. It's inference in a Gaussian process in linear time, and that's possible because it's not just a Gaussian process, it's also a Markov process. All right. So that's how these algorithms work. Yes?
Can I ask one more question about the previous slide? So can you go back, please? Yeah, so here we want to condition on something nonlinear, and if we do that, then we would lose Gaussianity. But we somehow change the nonlinear conditioning by a linear approximation. Yes, but we don't do this like we don't change the function f in the differential equation overall over the whole domain into some linear approximation. We do this kind of locally at every step.
Yeah, that's a very good point. No, so we do this locally, right? So we write at every time the solver takes a measurement, basically, it evaluates, like it has this local prediction that's actually called the variable m, right, or m minus. It's a local, actually, I mean, this is, let me go back to this picture, right? So once we're here, this is the prediction, right? We're at that point. So there's a vector field underneath here, and then around this point, we do a linearization. And then we do forward step again, and then around this point, we do a linearization, and then around this point. So this is it's a linearized model, but it's a model that designs the nodes of the linearization itself. So it actively chooses where to linearize.
Yeah, so this also answers my next question, like how do you linearize if your next step is a random variable? So you just take the mean of this random variable and linearize around the mean. Yeah, okay.
Exactly. And so this is a very good question. There are variants of these algorithms. There's also methods that don't linearize, but instead solve a quadrature problem at each step. So you integrate over the entire measure and evaluate f several times. That's then called the unscented Kalman filter rather than the extended Kalman filter. You could also draw samples from the distribution here. That's then called the particle filter. If you do that, then you can get non-Gaussian estimates. There's a corresponding paper by Philipp as well from Helsinki. And there's a final version of these algorithms that is like completely separate samples. So it's not even a filter anymore. And then you get like actual draws from a posterior that are totally non-parametric. They're also more expensive, of course, right? So there's a spectrum of these algorithms all the way from the minimal version is you don't linearize at all. You just assume you know the width of the distribution. Then that's like the fastest thing to do. The next level is extended Kalman filtering. That's actually I think the recommended way to do this, or at least in my opinion, which requires automatic differentiation or access to differentials. And then an increasing order of complexity, unscented Kalman filtering, particle filtering, and full Monte Carlo algorithms. So now, after I've told you how these algorithms work, let me spend a few moments telling you that they also exist. So when we started work in this domain like 10 years ago, so most of this was just like abstract mathematical questions, like what does it mean to think about inference in terms of, or computation in terms of inference. And then the first versions of these ODE solvers were implemented as actual Gaussian process regression, which obviously didn't scale. Then we moved to these filters. For quite a while, there was theoretical analysis was on the forefront to show that they have the right convergence rates and so on. But we're now in a phase where these algorithms are actually implemented properly. So if you like, there's a website called probnum.org, which contains access to a Python library that is relatively professionally developed. It's easy to install. It's also well tested. And actually, I can show you a few plots to show, and I really want to stress this because I know that this is a frequent problem when I talk about this, that people kind of think, it's a nice idea, but this is going to be so hard to implement, I don't want to deal with this. So let me tell you that these methods actually exist and that they work reasonably well. So here's an example plot from a paper that Nico Krämer, one of my PhD students, recently had conditionally accepted in JMLR, but you can find the preprint here. It's one problem that we talk about here, is like just as an example. This is a reduced three-body problem. So it's the path of a spacecraft that leaves from the moon and has to circle around the Earth, basically. It's a classic benchmark problem. And what you see here is a comparison to classic ODE solvers as implemented in SciPy. So there are two different Runge-Kutta methods. The classic one is the Dominant-Prince pair of order 5 with an error estimator of order 4. And the other one is a more exotic Runge-Kutta method of order 8. And here in this plot, you see a local error compared between the two algorithms. So we ideally want to be sort of on this dashed line. Actually, like the further we are to the right, the better, right? And we're doing better than the Python version. Here is global error. Again, you see things are really close to each other. Here is these algorithms relative to their tolerance. So this typical for these algorithms is that the user provides a tolerance level, right? How precise do you want them to be? And then they sort of are supposed to hit that tolerance level slightly above, which is actually typical for these algorithms, also for the classical ones. And then maybe the more interesting question is, so how well do they perform? How quickly do they converge? Both as a function of the number of times they evaluate the vector field and in wall clock time. So here is as a function of the number of evaluations. The thin lines in the back are the off-the-shelf solvers, and the thick lines are the new probabilistic solvers. So you can see that they can converge very fast, at least as fast as the classic solvers, and maybe more interestingly, they can also converge at very, very high rate. So up to order 11. So it's possible to implement these methods very stably. This is not straightforward. It requires some real thinking about what's going on. That's what Nico did for this paper. And then you can run them at extremely high order. Order 11 is so high that this is almost a vertical line. So basically, there's not much point in increasing the order further. And here, this is the slightly more tricky thing to sell. Here's the computational cost in terms of wall clock time. So you can see that there is still a gap. This is the same y-axis, by the way, here and there. There's still a gap between the probabilistic solvers implemented in Python and the off-the-shelf solvers in Python. Depending on how optimistic you want to read this thing, it's something like between a factor of 10 and a factor of 100 difference in runtime. We think we understand where this comes from. It's mostly very advanced software design. So these methods here do very smart memory pre-allocation to make sure they can efficiently, that they don't become I/O bound. We could potentially work on this here as well. That would also, restrict a little bit how the solvers can be implemented. So for research code, we kind of try to stay away from that at the moment. But so let me just really to drive home that point. If you're worried about the runtime of these algorithms, one other of my PhD students, Nathanael Bosch, recently ported these algorithms to Julia. So if you're a fan of the Julia language, then you can use probnum_diff_ect.jl for this. And here is a comparison on a simple non-stiff test problem, a Lotka-Volterra problem, of these methods in an error versus time kind of plot. So you kind of want to be down here, fast and good. And of course, as the error decreases, the runtime increases for all of these methods. And what you see in this plot is, in gray at the top, MATLAB code, standard MATLAB solvers, like commercial solvers, if you like. In green, Python packages, so SciPy. In blue, Fortran code, classic Fortran code, Hirers dopri5.f. And so I think these two here are C code, they're commercial solvers in C code. And these bright red are the Julia solvers, which are known to be super efficient. So they're very, very fast. And so the off-the-shelf Julia solvers, right? So diff_ect.jl. And what you see in fat orange are the probabilistic solvers. The point of this plot is to say the difference in runtime, yes, the probabilistic solvers in Julia are slower than the non-probabilistic solvers in Julia, but they are faster than the SciPy code for classic solvers and faster than MATLAB. So if you are the kind of person who doesn't need the ultra-fast speed of Julia code and is actually currently happy to use an ODE solver in Python, then you shouldn't be worried about these, the gap in runtime cost to the probabilistic solvers. And if you really want it to be faster, then don't worry about moving from probabilistic to non-probabilistic, but worry about moving from Python to Julia, basically. So the other question is, of course, are these solvers actually doing what they're supposed to do? So I claimed at the beginning that these solvers, they inherit good properties of the classic methods. And I actually say this, I want to stress this. The reason we can do that is that we are using a lot of insights from classic ODE solvers. So I'm really not arguing that we should ignore all of classic numerical analysis. Instead, we should extend it, right? Build interesting new stuff on top of it. But then I said there's also a new quantity, this uncertainty, and that is somehow calibrated. So let me show you a final plot for this. This is another paper that was in AI Stats this year, which you may not have noticed because Slava had such wonderful papers, but you know, like this was also at the same conference. It's about the calibration of these solvers. So what you see here is a plot plotted against the empirical error of these methods. So that's the tolerance level set by the user, basically. A plot of a chi-square statistic. So the statistic is the square distance between the actual solution and the estimated solution divided by the variance estimate of the solver. So what the solver thinks its error is. And the green region is a 99% confidence interval. So ideally, all of these lines should be in this green region. And what you see here is 6 different plots that correspond to 6 different ways of implementing these methods. And there's, of course, a sequence here where you kind of increasingly do more and more to get them better calibrated. That's the story of that paper. So at the end, kind of the bottom right plot is the one you want to look at. You can see that these solvers are arguably relatively well calibrated. Yes, they're sometimes just outside of that region. I mean, they should be out there like once in 100 times. They're maybe out there more like 5 in 100 times. But that is still actually a very good calibration, especially compared to the kind of error estimates you get from a classic solver. So not only are those solvers richer in their output language in the sense that you can draw posterior samples, they are also arguably better calibrated. And the way that this happens, that this works actually, is these methods adapt their step size, just like classic solvers, and they directly relate the step size to an error estimate. Right? Because why are you reducing your step size? Because the error is large, right? You decrease the step size until the error is within tolerance and then increase it again when the error stays down. Okay, so this section of the talk was intended to convince you that these methods are not just some mathematical idea, they actually work. And they exist and you can implement them if you like. Now, the final section of the talk is where I would like to convince you that they also do something really interesting. So when I started working in this field, I thought that plots like this would convince people that this is cool stuff and they should use it. It's like, why? Like, uncertainty is great, right? Everyone should want uncertainty. But actually, I learned that quite similar to Bayesian machine learning in general, it's not just enough to just have uncertainty, because you have to explain to people why uncertainty is useful. And I agree with that now. Actually, for ODEs, there's a particular problem that if you, most people actually solve ODEs not in this regime, right? But in this regime. They solve it to such a high precision that the error doesn't really matter anymore. You can barely see it, basically. In particular, so for example, like I showed you this plot here before, right? So if you make a line like this, the error bars, if you would plot them around this curve, they're invisible. So that is maybe not the key use of this kind of functionality. It's not just about adding error bars to a simulation. It may be sometimes, but not typically. Instead, in my opinion, the real killer application for these methods is the fact that they phrase this solution of the computational task as an inference problem using data. And that means that you can mix and match different kinds of data with each other. And now I'd like to return to this example that I made at the beginning of the talk. So in classic numerical analysis, as many of you will know, there is a pretty clear distinction between what you might call a forward problem or a simulation problem and an inverse problem. So the forward problem is I give you the ODE or the initial value problem or the boundary value problem, and the task of the algorithm is to return the solution, like the path, the trajectory of the dynamical system, X. And the inverse task is I observe trajectories of the system and I would like to know what the system is. So this is, by the way, also of course related to this kind of problem that I showed you before, right? We have a trajectory, we would like to know what beta is. Now there are of course methods to solve the inverse problem, both in a Bayesian and in a point estimate kind of sense. But what these methods always and invariably do is that they are built as a loop around the ODE solver. So actually, I can show you some code. So this is not my code, it's NumPyro. NumPyro is maybe one of the currently most advanced probabilistic programming environments. Very, very cool piece of software, so I don't want to diss it at all. I'm not picking it out to say this is stupid. I want to pick it out to say this is really great code and see how people do that and how it could be improved. So here's an example, a tutorial example from the NumPyro page for a predator-prey model, so a Lotka-Volterra type problem. Here's some data, so the dots are data. You'd like to fit this model that you see in this plot. So you observe data, trajectory of the dynamical system, you'd like to know what the ODE is. And here's the code for this. Let me maybe I can zoom in a bit so that you can see what's going on. In this code, they first define the vector field, so that's the ODE being written down. And then they build a model. And the model is, if you give me parameters theta, right? If you draw these, like this is the prior for these parameters, then you can solve the ODE. And here there's a call to an ODE integrator, to a solver, and a classic solver, a Runge-Kutta method. And then the main argument is actually you run Markov chain Monte Carlo on this thing, and that means you just call this model tens of thousands of times, basically. Every single time, you give it a new value of theta, you get a new observation, and what this essentially boils down to is that in this setting, right, you start with an initial guess for beta, you get a curve, that curve doesn't look like the data at all, so you compute a residual between the red curve and the estimated solution, and then compute a gradient using automatic differentiation and minimize that gradient. Minimize the distance, the residual. Yes?
Sorry, I think I get the idea, but why the number of tens of thousands of times? Isn't that too much?
Well, it actually, so, I mean, for this example here, the parameters are not that many, so this, I think, does like 1,000 solves or so. That's just how inefficient this optimizer is.
It's iterative process, isn't it?
Yeah. So
I mean you get closer to the solution on each step, and
yes,
about one order of magnitude closer. So in 10 steps, you're basically there.
Yeah, I mean, you can run this code. It uses way more than 10 steps. Oh, actually, so this is actually a Monte Carlo method, right? So it also draws samples. But even for optimization, so if I go back to this example, keep in mind that this
yeah, I get it now. Sorry. Okay.
So in this example, keep in mind that this is a function, right? So beta is not just a number we're trying to fit. We're trying to fit a nonparametric model, so some kind of Gaussian process posterior to this function, and it might have a lot of degrees of freedom that we might want to fit, right? But what kind of solvers are these people actually using? So they call a super cool, advanced, experimental automatic differentiation library, which I also have open here. So this is the ODE solver in JAX. And just to like drive home the point, what does it actually call? It calls a, where is it? Where's here, a Dorman Prince pair. So that's your classic 1986, basically like ported Fortran code by Ernst Heyrer, Runge-Kutta method. And so what is that? It's not actually a filter, but it has this property that it's a for loop, right? It starts from the beginning and then loops forward. So what this here does is actually it builds a double for loop. It does an outer for loop over the ODE solver, and then the ODE solver is itself a for loop, right? And every computer scientist knows that nested for loops are a bad thing. Is this nested for loop necessary? Well, no, because they are both observations of data, right? We would like to observe that the ODE holds, and we would like to also observe that we know what the trajectory of the system is. But there isn't really a reason to do one in a different way to the other. So if I go back to this example that I started the talk with, we would like to combine these two sources of information. We'd like to say that we know that there's this differential equation. There's just an unknown quantity in here, beta, that I don't know, that I have a probability measure over. By the way, notice that this beta actually enters linearly in this differential equation, which is very convenient. And secondly, I have this trajectory. So what the solver can now do, going back to the fact that it's a Kalman filter, well, I mean, the classic solver can't, because Runge-Kutta methods are not phrased as filters. They're somewhat like slightly broken in their structure so that you can't really think of them as a filter. That gives them other advantages, but they're, in my opinion, rather minor. But if you have a probabilistic solver, which is a Markov, Gauss Markov process, so it's a Kalman filter, which means it keeps track of both its point estimate and an uncertainty estimate. So that uncertainty estimate is the actual like operative quantity. Then what you can do is you can step forward through time, And if there's no datum, no data point, then at every time step, the solver can just observe this piece of information, this data point that the ODE holds. That's it. And then whenever it observes a data point along the way, then we just condition on that data point as well. And that's a different observation operator. So we observe not that the difference between the derivative and the evaluation of the vector field is 0, but we observe that the evaluation of the trajectory has this particular value. But both of those are straightforward for Gaussian processes, right? Because they're derivative observations or function value observations. And you can use the information gained from those data points to inform the solver about unknown quantities in its state space. So we can enlarge the state space a little bit and say, instead of just the states that contain the solution to the ODE, there is this extra quantity called beta, or in this plot it's called u, or in this figure, that is also unknown, and please infer that along the way as you go. So here's a picture of how this works. This is from a NeurIPS paper this year that is just coming out next week by Jonathan Schmidt, a master student in my group, and the aforementioned Nico Krämer. What you see here in this plot is, here at the top in black as dots, this data set again that I've mentioned before. It's now plotted a little bit more simply. It's the same data set. So this is the number of infected people basically over time. Here in the middle is the contact rate. So that's this thing we would like to infer, beta, the how often people meet and how much they meet. And at the bottom, it actually doesn't matter. So this is a plot involving vaccination rate in Germany, because in April, when we wrote that paper, we were very confident that the vaccination rate would go to 100%. We wanted to see what will happen in the future. We all know by now that was a bit too optimistic. So what we now see in this plot is, actually the plot is slightly constructed in the sense that at every point in time, so that you can see anything in the plot, you'll see the predicted solution of the ODE. So if you would run the solver from here on forward without ever conditioning on data, it would make this prediction. And you can see it's this crazy prediction for the dynamics of this differential equation that everyone was worried about in April 2020. And now what we can do is we can let the solver step forward individual steps, and in between two observations, it always just conditions on the value of the ODE. And whenever it encounters a data point, it also conditions on the value of that data point. So early on, those data points provide very little information, because the number of infected people is basically 0 in early 2020. And if there are almost no people in the population, that means almost no one gets infected. So you don't learn much about how often people meet, right? Because the only way to figure out whether people are meeting or not is if one person infects another person. But then as we enter the first wave, we see that the number of cases rises, but it doesn't rise as fast as it would rise under the prior for the contact rate. And so the only explanation for this is that the contact rate was falling during that time. And of course it did, because that was during the first lockdown in Germany when people didn't interact with each other anymore. Then there is the summer of 2020, which in Germany had very low case count. Basically, there was almost no cases for a while. And that again means that now we learn very little about the contact rate, because there are almost no people getting infected by each other, so we don't know how often people meet. Then the second wave hit, that was in winter last year, and we again learn about what the contact rate is and how it behaves over time. It goes down. There was a lockdown over Christmas. There was a pretty severe lockdown in Germany. And then the summer comes again, and we again see that people are beginning to meet more often. Then we reach the spring, and then the simulation ends. So what you've just seen is a single solution of an ODE. So it's a single forward path. If you would implement this model in something like nonpyro that I just showed you before, then solving with this data set for this kind of model with this nonparametric description of the contact rate would actually take something like a day or two on a normal desktop machine. You can run this code, not the code that made that plot, but the corresponding simulation, this forward simulation with the probabilistic ODE solver in a minute or two. So it's an actual genuine speed up in computation, not because probabilistic inference is easier than point estimation, quite on the contrary, but because the probabilistic framework allows combining these two sources of information in closed form, and therefore basically saves one for loop. And so what's, I think, conceptually nice about this is, so at the end, of course, you can do a backward pass and draw samples. So that's for free, basically. So you get these draws from the distribution. What you can maybe arguably see here is that this blurs the line between forward and inverse problems. So what we've done here is we've done in one fell swoop A provided an estimate for the ODE, so that's the inverse problem. But at the end, the solver can just continue running forward and make a prediction for what's going to happen next. And so that's a forward solve. There isn't really a difference anymore between backward and forward or forward and inverse. They are part of the same problem. Now, of course, actually, this is an approximate algorithm in a sense. So because early on, right, this was here based on predictions that aren't exactly what the underlying contact rate is. So what you could now do is you could do a second loop by basically moving the linearization points around a little bit to get a slightly refined posterior. We actually tried doing that, and it showed basically no further change. So this algorithm is essentially converged after one step. Right, so you can really think of this as getting rid of one for loop. Now, let me just, as a final point, notice that you could, of course, use the same idea to condition on all sorts of other information. Not just the fact that there's an ODE with an unknown quantity and that there are trajectories, but any other information about the curve that you can sufficiently linearize to include it in this framework. For example, you could condition on the fact that the system you're trying to simulate has some conserved quantities. That it's for example, symplectic, that there is some Hamiltonian that you know is conserved. So here in this plot, you see in black on the left, sort of a classic Henon-Hyles system. It's the famous example. This is a paper written by Nathanael Bosch, who I mentioned before, the guy who wrote the Julia library. So this is a high precision solve of this system, and you can see that it has this typical kind of orbit-like behavior with conserved energy. If you solve this system to relatively low precision with a probabilistic solver, then you get this kind of like rolled up bundle of wool kind of picture. This is also typical. You get a similar thing if you use a classic solver with low precision. But if you use the same low precision, yet condition the solver on the fact that that energy is conserved. So there's a function called the Hamiltonian, and we know that it's a function of the solution of the ODE, and its time derivative is 0. So that's another information operator to plug in. You get this plot on the right, which again, of course, is not exactly the same solution, and that's deliberate for this plot. Otherwise, it would be a boring plot, right? And you can make this plot look like the black plot by increasing decreasing the error tolerance of this method, but that would be a bit boring, right? But it conserves the energy. Now, you can use all sorts of other information. So for example, you can condition, and this is sometimes a difficult to understand trick, you can tell the solver that the ODE is actually may be of second order, for example. You may think that that's not actually information because any higher order ODE can be written as a lower order ODE, but it turns out it's actually still an informative thing to do, to tell the solver that there's a relationship between the states. You could inform it about algebraic equation properties. So, for example, mass matrix algebraic equations look like this, and various other things. And again, there are solvers for these problems. There are classic algorithms that do all of this, but they tend to be specific solutions for specific problems. So there are geometric integrators. There are symplectic solvers, but symplectic solvers typically can't, aren't used for inverse problems, for example. It's hard to find a symplectic solver that's also automatically differentiable, and so on. The nice thing about a probabilistic solver is that if you phrase it as a filter, all of these pieces of information can be jointly added. They can all be added as different observation operators without writing a new piece of code every single time. Okay, with that, I'm at the end. I've also, I think, kind of pretty much exactly used up the time. The main takeaways I wanted to make, also my blinds are going up, so you're going to stop seeing me in a moment because it gets too bright. The main points I wanted to make are that, first of all, it's a valid idea, in my opinion, and by now we have a lot of scientific work to show that you can think of computation as a form of inference, the active collection of data by a computer using the hardware of the computer. There is a mathematical framework for phrasing this process, and that's the theory of probability, essentially applied to numerical algorithms, probabilistic numerics, to quantify sources of uncertainty and information, so the opposite of uncertainty, arising in this process from all different kinds of sources, from knowledge from data, knowledge from computation, uncertainty from imprecision in the computation, and uncertainty from a lack of data. And as an example, I showed you the class of probabilistic ODE solvers, which you could call ODE filters, that start out essentially taking classic ODE solvers as a starting point. So they match their properties in terms of convergence rate and computational cost. and then add uncertainty as an additional functionality, that uncertainty has, like, in its explicit form in the algorithm, can then be used, among other things, to combine various forms of information, like conservation laws, like mechanistic knowledge about the ODE, and empirical information about the trajectory of the dynamical system, to do joint inference from multiple information sources. And that, to me, is the main draw of these kind of algorithms, that they kind of enrich the language of, or mix and match the language of inference and computation, so that one doesn't have to think separately anymore about them. If you'd like to know more about this, there's also basically all of our papers are on our website. There is a book coming out from Cambridge University Press that I wrote together with Hans Kersting and Mike Osborne. It's currently with the editor, so it should be out early 2022. And yeah, that's pretty much what I wanted to say. Thanks.